Going further, we are told that there is a rubber ball, and that what that rubber ball does, why we have that adjective rubber, is just telling us something, is that it's elastic. Has a mass of 50 grams. Now the 50 grams is not in standard units, so we're going to convert that right away to 0.50 kilograms. It's thrown towards a vertical wall. We see the picture below, so let's set up our coordinate system, plus and minus. So we have a speed of 20, a velocity of plus 20, and a speed afterward of 18 meters per second, a velocity of negative 18 meters per second. It bounces back with that speed. It's contact with the wall for 0.80 seconds, that's delta t. Calculate the change in momentum of the ball. So change in momentum of the ball, the simplest way for us to do that is to say that the change in momentum is P minus P0, which is mv minus mv0, and we can factor out the m like so. And our mass is 0.050. Final velocity is minus 18, and the initial velocity is 20. So that gives us 0.050 times a negative 38, which is equal to negative 1.9 kilogram meters per second, and that is the change in momentum. Checking our sign on this, for the ball, if it had come to a stop, it's going to need a change in momentum. And that change in momentum will be caused by a force in this direction. So the momentum it had that was positive becomes 0. So indeed, the change in momentum is negative. But it not only stops, it accelerates and goes in the other direction, additionally adding more momentum in the negative direction. So all the momentum is negative, negative 1.5 kilogram meters per second. Next, we want the average force acting on the wall. And we can go right to Newton's second law. The F net is delta P over delta T. We have a change in momentum of minus 1.9 and a change in time of 0.080, which gives us minus 23.75 newtons. We can only report two significant digits, so that's minus 24 newtons is the average force. Now notice our formula F net did not say average force. It's the net force. We could have started out with the impulse and said I is F bar delta T, in which case we would look at F bar, and that would give us I over delta T. And what we know is the impulse imparted is equal to the change in momentum received, so we have delta P over delta T, and it's the same answer. Lastly, we're expected to suggest in terms of Newton's third laws, which we've already specified, N1, N2, and N3, why a steel ball. All right, so that's steel ball versus a rubber ball. Same mass, same initial horizontal speed exerts a greater force on the wall. Well, if force is delta P over delta T, to make force larger, either we could have a greater change in momentum, or we could have a shorter time. Now, the change in momentum is going to be m delta v, and we're told that it has the same speed, so 20, and it ended up minus 18. So I suppose it could be 20 and end up being 20. That would give it a greater delta v. Or we could have a smaller delta t, less time in contact. Well, if we think about a rubber ball coming in contact with a wall, that rubber ball will compress because it is elastic, that rubber ball. What that serves to do is to increase the time. Whereas we have a steel ball, it is rigid. It hits the wall and bounces off. It's like a billiard ball, a pool ball, compared to a tennis ball. The tennis ball hitting the wall will take some time to compress and then expand, whereas the billiard ball or the steel ball will not take that time. The delta T is small. All right, so Newton's laws of motion. So we would say Newton's second law states F net equals delta P over delta T. Assuming the same delta P, a smaller delta T will yield a greater force. Since rubber is more elastic than steel, the collision or impact will take more time than the more rigid steel ball. Thus, the steel ball will take or spend less time in the collision with the same delta P, producing a greater force. So we have used Newton's laws. Same initial horizontal speed. There's just one thing we're kind of fudging here, which is that the final velocity will also be the same. But in any case, we've explained how that would happen. Whether or not the velocity goes from 20 to minus 18, or 20 to minus 19, or 20 to minus 20, this is with the rubber ball. The larger and more important part of the change has to do with the time. Since we're not given the final velocity, we really shouldn't comment on it. And what we did is we explained ourselves saying the same delta P. And that's B14.